were the averages. Okay, now everybody's feeling better, right? You got your results, you're like, oh my. These were the average scores. Okay, that was a hard exam. That was a very hard exam. And the purpose of that exam was to tell you where to focus the rest of your time as you're studying for your board exam, right? Now, if you scored over 95% on all 5 sections, I want you to send me your resume because I'm hiring you. Actually, nobody scored over 95%. If you scored over 85% on all 5 sections, you might as well log off now because you are good to go. You are ready and nobody likes you. No, I'm kidding. There is actually one person that scored really, really high on all 5 sections, and that was amazing. Now, if you scored between 75 and 85%, you're in a great, great position. Okay, I'm glad that you're here. You'll get something out of this. But of all the clients that I've worked with individually, everyone that scored over 75%, okay, I'm sorry, everybody that scored over 75% on this mock board exam passed their board exam. So if you got that, that's the magic number, 75%. Now, if you're between 65 and 75%, you're close, okay? You're very close. We'll get through today. If there's some additional things you want to work on, I've got some courses on my website, some mini courses here. Are you guys able to see these mini courses? Yeah. So, maybe you did really well in all the sections except instrumentation. I can give you some one-on-one instruction with instrumentation. All of these courses come with materials. It comes with a recording, and it is live, just like we're doing today, okay? So I've got courses for all 4 of these sections. I also have a 2-hour math boot camp if you find that the math is what you're struggling with. And then I also have clinical procedures. So if you're between 65 and 75, focus on the one area that you're the lowest. And if you're the same in all of them, focus on clinical procedures because that's the biggest part of the exam. Now, if you are under 65%, my recommendation is to set up a 15-minute free call with me, okay? And what I will do, this is absolutely free, no obligation to anything. I will look at your individual mock board exam and I'll write a detailed analysis on what you need and I'll make a recommendation because you want to be successful. You've spent too much time and too much energy and too much money to not pass that exam. So set up a free 15-minute call with me and we will get you to where you need to be. All right, so these were the averages. And now we're going to jump into the actual questions, okay? So we broke this up into the 5 sections. We're going to do physics first. So first question is, gallium-68 has an atomic number of 31. And the question is, how many neutrons does it have? So what we have to understand is what this gallium-68 is. The 68 is the mass number. That's this number here, the A. A stands for all. I'm kidding, it's an atomic mass number. But you can think of it as standing for all, because it's all, everything in the nucleus. So that means that that number has total of 68 nucleons. If it has an atomic number of 31, that means it has 31 protons. All we have to do is subtract that. 68 minus 31 is 37. All right, I need to get my answer key in front of me because I want you guys to think I'm smart, but the truth is I have all the answers in front of me. All right, next question. Conversions are next, all right? 70% of nuclear medicine math is conversions. If you can convert and decay, you're golden, okay? So I'm gonna go through a couple of conversions. I'm gonna start out easy. We're gonna convert 1 rem to millisieverts. Now, one thing that we have to remember is what our conversions are. Conversions are something equals something. And we need to know that 100 rem equals 1 sievert, all right? By the way, 100 rad also equals 1 gray. Those are the easiest conversions. So if we know this, I also think of conversions as doorways. If you're in your house, you have to walk to your doorway before you go through the doorway. So we have to get to our doorway. Now, in this problem, we are at our doorway. So we're starting out with 1 rem, and our conversion is in rem, so I can simply put my 100 rem down here, all right? And whenever you're doing a conversion problem, if you get stuck, just the very first step is always whatever's on top, goes on bottom. Just do that first. And then we'll put 1 sievert here. Rems cancel. I'm at sievert, but I'm not done because I have to go to millisieverts. So my next step, again, whatever's on top goes on bottom. From sieverts, I can convert to millisieverts. There's 1,000 millisieverts and 1 sievert. Sievert cancels. I'm left with millisieverts. Pull out your calculator. By the way, I recommend 2 calculators. This isn't a commercial. I'm not getting any royalties from this. But the 2 calculators I recommend is this one, because it's easy and it's cheap. But if you're going to take the ART exam, you want this one, okay? Because the ART has this exact calculator that you will use. It won't be a physical one, it'll be on the computer. But you want to know where your buttons are. All right, so you punch that into your calculator and you end up with 10 millisieverts. Moving on. Now we're going to convert 80 millicuries to gigabecquerels. So we need to be able to convert between units of activity. So you have to remember at least one conversion between the two. And the one I recommend memorizing is 1 millicurie equals 37 megabecquerel. Why? Because that's what most of our doses are. Most of our doses are in millicuries. And so that's the easiest and the fastest conversion to do. So again, with conversions, we start with what we're given. Whatever is on top goes on bottom. We're at our doorway, so we can go ahead and use our conversion. 1 millicurie is 37 megabecquerel. Millicuries cancel. And I don't know if you can hear my doorbell right now, but my neighbor decided that this is the best time to cut their grass right when I'm doing this webinar. So every time he walks past, you're going to hear that again. All right, millicuries cancel. 80 times 37, your answer here. Oh, we're not done, are we? I was distracted by my neighbor cutting his grass. We have to get to gigabecquerels, so we're not done. We're only at megabecquerels. Whatever's on top goes on bottom. We can go directly from megabecquerels to gigabecquerels, knowing that there's 1,000 mega in 1 giga. Mega cancels, I'm left with giga, where I want to be, and our answer comes out to 2.96 gigabecquerels. All right, one more math problem, then we're going to get away from math for a second. So now we're going to convert 2.3 microcuries to disintegrations per minute. This is a big, long problem, unless you've memorized a conversion. One conversion you may or may not memorize, okay? I'm going to give you the conversion, but then I'm going to show you how to do it if you forget the conversion. 1 microcurie equals 2,220,000 disintegrations per minute. So if you know this conversion, you can simply start with your 2.3 microcuries. Whatever is on top goes on bottom. I need to put my conversion in 1 microcurie. It's 2,220,000 disintegrations per minute. Microcuries cancel and the disintegrations per minute, and I get this answer right here. But what if, you know, I get in there, I'm taking my actual board exam, and I freeze up. I have no idea what that conversion is. You can still figure this out, okay? So I'm going to show you how to figure this out the long way. We're going to start with 2.3 microcuries. I know that disintegration per minute can convert to disintegration per second. And by definition, 1 disintegration per second equals 1 becquerel. And I also know that 1 millicurie equals 37 megabecquerel. Why is that important? Because these are my 2 conversions. These are my doorways. I have to get to the doorway before I go through the doorway. So I'm going to start with 2.3 microcuries. Whatever's on top goes on bottom. Microcuries on the bottom, millicuries on top. There's 1,000 microcuries and 1 millicurie. Microcurie cancels. Now I'm at millicurie, so I can go through my doorway. Whatever's on top goes on bottom. Millicuries on the bottom, megabecquerels on the top. 1 millicurie is 37 megabecquerel. That's my conversion. Millicuries cancel. I'm not done though, because I have to get to becquerels before I can get to DPS, before I can get to DPM. Memorizing that conversion is becoming a whole lot attractive right now. A lot more attractive right now. All right, so I'm going to go from megabecquerels to kilobecquerels. There's 1,000 kilobecquerels and 1 megabecquerel. And then from kilobecquerel, I can go to becquerel. There's 1,000 becquerels and 1 kilobecquerel. Now I'm at becquerel. That is equivalent to a disintegration per second. I'm so close. I have to get to DPM. Whatever's on top goes on bottom. This right here is where all the mistakes are made. The conversion between DPS and DPM. Everybody wants to put 1 minute is 60 seconds. That's wrong. Instead of thinking about disintegrations per second and disintegrations per minute, think about dollars. Okay? That's the universal language, dollars. If I give you $1 per second, you have $60 per minute. It's as easy as that. DPS cancels, I'm left with DPM. Before I throw this in my calculator, I'm going to find 1,000 on the top, I'm going to find 1,000 on the bottom and cross them out. Multiply across the top, you're going to end up with this number. And if you multiplied 37 times 1,000 times 60, you end up with that 2,220,000 DPM equals 1 microcurie. All right, it's a lot of math. Make sure you know all this stuff, okay? Make sure you can convert up, convert down. Make sure you know all your conversions before you go and take the test. Next question. How are I-123 and I-131 related? So the answer here is they are isotopes. And I know very quickly they're isotopes because they're the same letter. They're the same element. Isotopes by definition are the same elements. You know, all the time, interchangeably, we're like, we're going to inject you with a radiopharmaceutical. We're going to inject you with radionuclide. We're going to inject you with radioisotope. And you know, if you talk to many of your technologists, they have no idea what the difference is between them anymore. But you as a student have just learned this. And so they are slightly different, okay? So nuclides, this is how we describe all of our nuclides. Isotopes, isotones, isobars, or isomers. Okay? Isotopes, same number of protons, therefore they're the same element. Isotones, absolutely useless. We're not even going to talk about them. I don't know why we teach them other than to have another question on the exam. They're just the same number of neutrons. Isobars, the same A. Remember, A is all. That's the same number of nucleons. That's the number. So, if you had a question, gallium-67 and gallium-68, how are they related? They're isotopes because they're the same element. If you had a question, strontium-82 and rubidium-82, how are they related? Those are isobars because it's the same number. That's all you have to know. Right? Isomers, same everything, except one has a little M next to it. All right, back to some math. You have an I-123 capsule that has 420 microcuries. I want to know how long before it has 170 microcuries. So we're not solving for A sub T and we're not solving for A sub O, we're solving for T, which makes it just a little bit more difficult. We're going to set up our equation and we're going to take advantage of, we're graduated now, and we don't have to do any of those essay tests anymore that our instructors gave us, all right? It's multiple choice. And so we're going to learn how to use multiple choice to our advantage. So we'll set this up. We have 170 microcuries equals 420 microcuries. E to the negative 0.693 divided by half-life of I-123, make sure you know all your half-lives, 13.2 hours times T. We're going to solve for T. We don't know what T is, but we know it's one of these. And I can show you how to solve this. I make my students learn how to solve this so they can do it on an essay test, but we don't have to because this is multiple choice. And one of those answers is going to be this letter. So what we're going to do is we're going to be smart about this. We're not going to pick the top one. We're not going to pick the bottom one. Not because they're not the right answer, but we can rule out more if we pick one in the middle. So what we're going to pick is we're going to pick 16 hours. So we're going to put 16 in here, and we're going to solve this side to see if we get this answer. So if you have your calculator, throw that in your calculator real quick. 420 second ln negative 0.693 divided by 13.2 times 16. And what you should end up with is 181. So what does that mean? That's too much activity. I'm trying to get down to 170. So that is not enough time. So this is wrong. But also that one's wrong too. So I was able to rule out two of them. So now I can pick this one. I'll put 18 in there. And when you do that, it comes out to 170, so that is the correct answer. And if it didn't come out to 170, then you knew that one was. So use that to your advantage. All right. Radionuclide parent has a mass number of 223. When it decays, the daughter has a mass number of 219. And the question is, what type of decay has occurred? Well, the only time that we are going to lose a mass of 4 is with alpha, because alpha is 2 protons and 2 neutrons. And so 4 minus 4 equals 219. That's all we needed to know there. So alpha decay. All right, so here's what happens. This is radium-223. It is the only approved alpha emitter that we have so far. Hopefully there'll be some more soon. Radium-223. It actually has 88 protons. It decays. This becomes 219. This is going to go down by 2, right? Because alpha is 2 protons and 2 neutrons. So that becomes 86. And if I were to look up 86 in the periodic table, it would say radon. All right. During beta positive decay, the number of protons do what? So make sure that you can write this down, okay? And maybe you want to write it down with me. If you have too many protons, a proton is going to turn into a neutron. And if you have too many neutrons, a neutron is going to turn into a proton. That's the only possibilities, because that's the only thing that's in the nucleus. And by the way, this is isobaric decay. Because when a proton turns into a neutron or a neutron turns into a proton, the A stays the same because the A is the total. Now, this side is positive. If I want to make this side positive, I add a beta positive. So now neutral plus positive is positive. They equal each other. This side's neutral, this side's positive. I need something negative, beta negative. Positive and a negative equal a neutron. And then there's the third one, right? Where a proton does turn into a neutron, but it does that by capturing an electron. So now you have proton plus electron equals neutron. All makes sense now, right? All right, so the question was, during beta positive decay, what happens to the number of protons? This is beta positive decay. A proton turned into a neutron. Therefore, we lost a proton, decreases by 1. All right. So here's what happens. Again, in beta minus and beta positive decay. Neutron turns into a proton plus an electron. Proton turns into a neutron plus a positron. And an electron, or a beta negative and a beta positive, are exactly the same, except one's positive and the other's negative. Exact same mass, everything. All right, we made it through physics. Let's touch radiation safety. All right, I love this chart because it kind of explains everything all together. So we have non-stochastic, which is also called deterministic, and stochastic, which is also called probabilistic. What does that mean? With non-stochastic, the dose determines the response. With stochastic, the dose increases the probability of the response. So they're two totally different things. So deterministic responses are things like skin turning red, losing hair. These three, that's acute radiation syndrome. We know how much radiation causes these things. And if we give you more radiation, it makes these things worse. That's what non-stochastic is. Now, stochastic or probabilistic, you increase the dose there, you increase the probability of it happening. And that's what ALARA is based on. ALARA is based on the probability of getting cancer. So as the dose goes up, this is dose, the response, or vice versa. So our question here was, ALARA is based on what model? And it is based on this model here, which is the linear no threshold model. This is the stochastic or probabilistic This is about, because the thing is we know we're not getting this much because our limits are way less than us getting any of these things. The reason we monitor our radiation is for cancer risk. Okay, so it says any increase in dose increases the probability, but it doesn't increase the severity. Okay, so it'll increase the probability of getting cancer, but it doesn't make you get worse cancer, or it doesn't make the cancer worse. All right. Which system will be affected if someone is exposed to an acute radiation exposure of 100 to 200 rem? By the way, that's the minimum amount of radiation you can get all at once and get acute radiation syndrome. And it depends on which book you're reading. One book says 100 rem, another book says 200 rem. Nobody really knows because it's not exact. So the answer here is the hematopoietic system. Hematopoietic, that's the blood-making system. That's that. So whenever somebody gets radiation therapy or radionuclide therapy, we're going to watch their CBC, because that is the first thing that's going to be affected in the patient, is their blood counts are going to go down. Hematopoietic. All right. Technologists received a letter from the radiation safety officer stating they exceeded ALARA 1 for the second quarter. I work with a lot of different students, and a lot of students are like, I have heard of ALARA, but I've not heard of ALARA 1 or ALARA 2. So ALARA 1 is 125 millirem per quarter. These are quarterly amounts, not annual amounts. And ALARA 2 is 375 millirem per quarter. Now, these aren't just made up numbers. This actually is 10% of the quarterly limit. That's my cat, by the way. That's Rankin. My other cat is Becquerel, so you might be able to see that one come by as well. ALARA 2 is 30%, okay? So, which of the following is true? Does the technologist need to take some time off? I think we've all exceeded ALARA 1 at one point or another. An investigation needs to occur, but no action is required. Technologist needs retraining, or the technologist received 375. Well, ALARA 1 is 125, so we know that's not correct. Now, when you exceed ALARA 1, your RSO should notify you. You should actually get notification in writing, but they should come and say, hey, you exceed ALARA 1. What's going on? You're like, well, I worked some extra hours and, I had a lot of patients. Okay, well, try to be more careful. Okay, that's it. But if you exceed ALARA 2, now action has to occur. It's like, okay, you need to do less patients, or we need to get you some help so you're not exposing yourself to that much radiation. So there's a lot in place to prevent us from getting anywhere close to the annual limit. Okay, a patient is receiving radionuclide therapy. If anyone is likely to receive 500 millirem, what action must the radiation safety officer or authorized user take? So 500 millirem is the maximum amount that the family of a radionuclide therapy patient can get. So if somebody's likely to get more than 500, they can't go home, okay? And the radiation safety officer will look at the patient's living conditions, the amount of exposure the patient's putting off, the occupancy factor of who's taking care of them, how long they're going to be around them, to determine that number. And if they determine that their caregiver is going to be more than 500 millirem, then they stay in the hospital, inpatient therapy. All right, a minor radiation spill has occurred. This has happened to all of us, okay? This is where you're injecting somebody and you drop a drop of technetium on the counter. After you decontaminate the area, you perform a removable contamination survey, fancy word for a wipe test. You put the wipe in the well counter. It reads 945 counts per minute. Background is 15. Efficiency is 64. What should you do? Well, first I'm going to calculate what my DPMs are, because CPMs are meaningless. We need to know how many DPMs are. So I'm going to take my 945 CPMs, subtract the background, divide that by my efficiency. And when I do that, I end up with 1,453 DPM. So what am I going to do? I'm going to document that. Why? Because it's less than my action limit. So once you decontaminate and you're below your action limit, you're done. You don't have to keep going. You're done. So these are suggested trigger levels. And I know that there's a textbook out there that we are all using that says 22,000 DPM. That's wrong. It's 2,200. Okay, 2,200 for both restricted and unrestricted. Now the survey level is going to be different for restricted versus unrestricted. And the reason is with removable contamination, it doesn't matter if you're in restricted or unrestricted, because that can be removed and moved from a restricted to an unrestricted. But surveys are going to be a little bit different. You can have more in a restricted area. All right, which of the following is notice to employees? This is actually NRC Form 3. This is what it looks like. Notice to employees. We've probably all seen this in our departments. And we've all read it, right? I've never read it, but I will summarize it for you. What this says is, hey, employee, you are working in an environment where you're going to be exposed to radiation. So here is this notice to you to let you know that. And here's my responsibilities to you. I'm going to give you the controls needed to protect yourself. But you're also responsible to me in utilizing those controls. So that's basically what it is. It's like an agreement, right? So now you're probably asking, what is NRC Form 4 and NRC Form 5? Did she just make those up? No, I did not. So this is NRC Form 3. NRC Form 4, this is prior dose determination. So if you worked at Hospital A for 6 months and then you go to work at Hospital B, you can't just walk in Hospital B and say, oh, well, at my last job I had 85 millirem total. They can't trust you, okay? Not that you're not trustworthy, but they can't trust you by law. They have to get this form filled out by your prior employer. Otherwise, they have to assume you got the maximum amount in that 6 months, and you're starting at 2,500 millirem. You only get 2,500 more. And we don't get anywhere close to that, so it's not a big deal. But these are regulations that span all workers that are exposed to radiation, and you know, we're actually a relatively low exposure. So that's what happens. That's Form 4, okay? Form 5, this is your annual dose report. Annual dose report. Did you know your employer is only responsible for giving you your dose report once a year? That's it, once a year. And it's through Form 5. And tomorrow we'll get into all of the different units, deep dose equivalent, committed dose equivalent, all the different units, but that's what is listed on there. All right, which sign should be posted in an area where an individual may receive more than 5 millirem, 30 centimeters from the source? So don't just memorize these numbers, think about what these numbers mean, because this question can be worded differently. This question could be worded, what sign should be posted in an area where an individual may receive 45 millirem? And if you just memorize this number, like, well, what does that mean? That is more than 5 millirem. That's 5 to 100. Because once you get 100, now this sign has to be posted, high radiation area. Okay? So caution, radiation area is between 5 and 100. Over 100 is this one. Both of them are 30 centimeters from the source. All right. This sign has to be posted in all of our departments because we're using radioactive materials. And we're going to add this sign if we have a CT attached to our PET or our SPECT. Technologist stores radioactive waste in a closet. How long does the waste need to be held prior to disposal? If you're studying from any old materials, you might want to say 10 half-lives, because that is the old requirement. When I say old requirement, I'm talking 2002 requirement. So why do some of our departments still hold on to that? It's not because they're stubborn and they can't change. Here's what it is. In 2002, the NRC did a complete overhaul of the regulations. And the reason I know this is because I lived through it. I graduated in 1996 and I learned all the regulations. And then in 2002, not much longer after I graduated, I had to relearn all the regulations. Well, when the NRC redoes their regulations, they send them out to all the agreement states. And most of us live in agreement states. And the agreement states can adopt the new regulations or they can be more strict. And many of our states decided to hold on to that 10 half-lives. So that's why you're probably still hearing 10 half-lives. But the answer is not that. The answer is until background levels are reached. All right, which label should be on a type A package that has a surface reading of 0.4 mR per hour and a transport index of background? This one's super easy because it doesn't have a transport index. Now look at these placards. On radioactive yellow 2, you see this box here? You see this box here? That's the transport index box. There's no box on white 1 because white 1 does not have a transport index. So super easy. If there's no transport index, it's a white 1. If it's transport index of anything, it can't be a white 1. Now, what is the transport index? That is your 1 meter reading. But that's not just a made up, like, let's just see what it is at 1 meter. That is for whoever's transporting, because these are all DOT regs. That's for whoever's transporting the radioactive material. They're assuming they're going to be 1 meter away. And what exposure rate are they getting at 1 meter? Which, by the way, fun fact, the cord of the GM meter is 1 meter. Okay. All right. Okay. So, at the beginning of this meeting, I made a critical error, and I did not introduce Sarah Gibbons to you. Sarah, do you want to turn on your camera? Sarah is helping us out. She is answering all the chat, and we have matching shirts on today. And fun fact about Sarah Gibbons is Sarah's my boss, okay? But she used to be my student. So I always tell program directors, be nice to your students because you never know when one of them's going to end up being your boss. But actually, Sarah's amazing. She's helping us. If you have questions, please put them in the chat. If you have any technical difficulties, Sarah will try and do that, and I will try and not be distracted by when they come up. Sometimes I do get distracted. Thank you for joining us and helping us, Sarah. Okay, so anytime no transport index, that's going to be a white 1. If there's a transport index, it's going to be yellow 2 or yellow 3. And then you can simply look at this right here. If the transport index is less than 1, it's yellow 2. If it's greater than 1, it's yellow 3. Super easy. All right, a technologist is performing radionuclide therapy for hyperthyroidism. This was a really highly missed question. The prescribed dose is 120 millicuries of I-131, and the technologist only administered 90 millicuries. So the first thing I'm going to do here is I'm going to say, okay, this is a radionuclide therapy. Therapies are plus or minus 10%. So I'm going to figure out what is the dose range that she should have administered. And so the dose range here, so 10% is going to be 12. So 120 minus 12 is 108. And 120 plus 12 is 132. So that's where she was supposed to administer. And if she doesn't administer between that amount, that is an error. Okay? That's an error. But this is also a therapy. And even though it's a therapy that was too low, it's still a therapy and an error, which makes it a reportable event. Okay, reportable event. It doesn't matter if it's too high or too low. You can do damage by giving a patient too little of their therapeutic dose. And so this is a reportable event. So what's a reportable event? That's when you have to call the NRC and you're like, I screwed up. Here's what I did. That does not mean you're going to lose your job and get in trouble or go to jail or anything like that. That's not what that means. We make mistakes because we are human. Now, the two professions that aren't allowed to make a mistake, the two professions are people in medicine and pilots, right? We don't want our pilot making a mistake. But the thing is we do make mistakes. That's why we have protocols. If you follow a protocol and a mistake occurs, it's not your fault. And you should argue that with your employer. The fault was with the protocol. The protocol was wrong. Now, if you don't follow the protocol, then it's your fault. You didn't follow the protocol. Okay? And that's why in medicine, we have a safe environment where we can report mistakes, because if a mistake is made, we need to change the protocol. If we're not in a safe environment to report our mistakes, then how do we ever change the protocol? So this is a reportable event. You're not going to get in trouble unless you didn't follow protocol, but it does have to be reported to the NRC. All right, that brings us to our third category, radiopharmacy. All right, what is the radionuclide impurity of an eluate with 94 microcuries of moly and 758 millicuries of tech? Do you ever notice almost everything in nuclear medicine? It's like, okay, here's the rule, but we're special and we're an exception to the rule. It seems like there's so many areas, like transient equilibrium. It's like transient equilibrium, the daughter is supposed to have more activity than the parent at equilibrium, but that doesn't happen because we're an exception to the rule. Well, this is another place we're an exception to the rule, because by definition, if you're looking at the radionuclidic purity, you want to know the percentage of radioactivity you want over the total radioactivity. But if we did that with moly tech, it would always be 99.9999%, and that number is meaningless. So our exception is that we are allowed 0.15 microcuries of moly per millicurie of tech, which is fine, but that's also not the answer, okay? Because the answer is, what is the radionuclidic impurity in this particular example? So we're going to take our 94 microcuries and divide that by 758 millicuries, because our radionuclidic impurity is going to be reported in microcuries of moly per millicurie of tech. And when you throw that in your calculator, and I'm sure you're all calculating along with me, it's 0.12 microcuries of moly per millicurie of tech. And how do we do that test? Well, we're going to use something called a moly shield. I wish it wasn't called a moly shield. I wish it was called a technetium shield. Why? Because it doesn't shield the moly, it shields the technetium. You put the vial in here, the vial of your eluate, put it in the shield, you put the cap on it, and you hope there's not a gap in the shield, because then you're going to fail radionuclidic purity testing. And what the shield does is it stops the low energy technetium and allows the high energy photons of molybdenum to be measured. So when you put it in a moly shield, it reads the moly. You take it out, it reads the technetium. All right, a moly tech generator was last diluted 24 hours ago. At the time, it had 3,500 millicuries of moly. The 24-hour tech moly ratio is 0.87. What is the theoretical yield of technetium? So this is done when you're in a pharmacy and you have 4 or 5 generators, and you're like, oh, I need this much technetium. Which generator should I milk? And when we have technetium shortages, they're doing this to make sure that they get the most possible technetium possible. But we have to think about what's going on. In that generator, we have molybdenum that's decaying. Here's our decaying molybdenum, okay? And at the same time that it's decaying, technetium is being made until you hit equilibrium, and then they decay together. And in this problem, it says that at this point here, we had 3,500 millicuries of moly. And it wants us to find out 24 hours later, right here, this is 24 hours, it wants us to figure out how much technetium is there. And the green is technetium, okay? Well, we can figure out the molybdenum easily by decay. A lot of you forgot to decay. A lot of you took this 3,500 and just multiplied it by 0.87. But you have to decay the molybdenum first, because in 24 hours, you're going to have less. So if we figure out how much molybdenum we have first, we can throw that into our decay equation. And the half-life of molybdenum depends on which book you're reading, anywhere between 66 and 67. I used 67. And we're going to multiply that by 24 hours. So when we decay our molybdenum, throw that in your calculator real quick, see if you get the same answer I do. Gives me a chance to take a drink. It's just water, I promise. Thank you for the laughing emoji, Sarah and Tanner. All right. So what we end up with is 2,730 millicuries of molybdenum. That's this right here. But we need to know this. But we're given the ratio, 0.87. So all we have to do is multiply that number by 0.87. And our answer comes out to 2,376 millicuries. All right. That is theoretical yield. That's like, in theory, here's how much I think is in this generator. That's different than actual yield. If the generator has a theoretical yield of 845 millicuries, and you milk the generator, and you get 798 millicuries, what is the efficiency of your generator? The efficiency is going to be what you actually got divided by how much is in there. We're going to multiply that by 100 because we want to put it into a percentage. If you throw that in your calculator, you should end up with 94%. All right, next question. We're still in radiopharmacy. When technetium is eluted from the generator, how many oxygen atoms are attached? Okay, how many oxygen atoms? So I think some of you saw 7 and you picked that. This is in a +7 oxidation state. And some of you picked 4 because for many of our radiopharmaceuticals, we reduce the +7 to +4 before we tag. And that's incorrect also. No, that is correct, sorry. 4 is actually the correct answer, but I was right that you do have to reduce it to a +4 or +5 oxidation state when you're tagging. I got ahead of myself. So it is we are attaching it to 4 oxygen molecules, and that's why protectinate can also be written like this. TC04 negative, 4 oxygen, and it is negative overall in a +7 oxidation state. And without a chemistry background, that's incredibly confusing. All right, next problem, production. Copper 64 is made in a cyclotron with this reaction. What is the target material? And even though you don't know that it's nickel, it has to be nickel because that's on all the choices. You can figure this out by the number. And remember, that's the all number, okay? That's the all number. So the way that this is written, copper 64, it's made proton in, neutron out. And we know on this side, we have nickel, because that's in all of our choices. And we're trying to figure out what this number is, okay? Now, when this is, these parentheses, when you see this, what that means is the first one is what comes in, the second one is what goes out, okay? And this number represents all. So it represents protons and neutrons. So if I'm adding a proton and subtracting a neutron, this number stays the same. And the answer is nickel 64. Now sometimes you'll see this reaction where it'll be proton in, 2 neutrons out, which is our next example, by the way. Indium-111, Z equals 49. I went ahead and wrote that down here. It's made in a cyclotron with this reaction. 1 proton in, 2 neutrons out. And the question is, what is the mass number and the atomic number of the target? By the way, this is the target, this is the product. Okay, that means that in the cyclotron, your target's out here, and the one we're used to is 018, right? And the particle comes in and slams into the target and becomes F18. So the target is what you're slamming the particle into, and the product is what you end up with. So in this particular example, I'm going to look at the protons first because I think that's easier. So I know that I added 1 proton to get to 49, which tells me that this has to be 48. So now I know it's either this one or this one. And now what I can do is I can just like take this number and say, okay, if it's 112, just hypothetically, if it's 112, I'm going to add 1 proton, making it 113, subtract 2 neutrons, making it 111. If I thought it was 113, add a proton, which would make it 114, subtract 2, which would make it 112, so it tells me it's not 13. That's the correct answer. Again, these are hard questions. All right, so I think we'll skip on that and we'll talk about that tomorrow. All right, a radionuclide is commercially produced in a reactor. What is the most likely way it will decay? Now, in a cyclotron, we add a proton. In a reactor, we add a neutron. Okay? And just as a sidebar, when we're adding a proton, we have to speed it up. When we add a neutron, we have to slow it down. So they're just like opposites. So, it's made in a reactor. How will it decay? It's going to have too many neutrons, right? And how does it decay with neutrons? Neutron turns into a proton plus a beta negative. Make sure you can write that down. Practice that tonight. So we know it's beta negative. Well, beta negative is in 3 of our answers. So this one is not correct. Now we have to figure out beta positive electron capture. Well, we know beta positive electron capture come from too many protons, and that's made in a cyclotron. So it can't be those either. So it has to be this one. Okay? Now, commercially produced is important because you can make beta negatives in a cyclotron, right? It is possible to do that. It is possible to make things many different ways, but when you talk about commercial production, beta negative is going to be made in a reactor, beta positive is going to be made in a generator or a cyclotron. All right, mechanism of localization. Make sure you know all your mechanisms of localization. And by the way, on my website, I have a member dashboard that has all of the flashcards, and there's a section for mechanism of localization. And if you go on the dashboard and sign up, I'm going to give everybody free access who's on this webinar today, okay? And so there's some other free resources on there as well. So mechanisms of localization, make sure you know that for every single radiopharmaceutical. For this particular scan, this scan is a DAT scan. And one of the things I always tell students when you're thinking about mechanisms, think about 2 things first. 1, compartmental, because there's a lot that are compartmental. 2, receptor. Because if you can name the receptor, you know it's receptor binding. Estrogen receptors, prostate-specific antigen receptors, somatostatin receptors, dopamine receptors, which is what you're seeing here. So if you can name the receptor, the mechanism of localization is receptor binding. All right, mechanism of localization for this one. I also like to ask, when I put a question like this, like, okay, what radiopharmaceutical was used? So being able to identify radiopharmaceuticals based on images is another important thing to do. So this is a xenon scan, obviously. It's not a DTPA scan because we see the washout. So what is the mechanism of localization here? That is going to be compartment, because we're taking the radiopharmaceutical and putting it into a compartment. In this case, it's the compartment of the air spaces in the lungs. The other compartments are gastric emptying, the compartment of the stomach, GI bleed, the compartment of the blood vessels, cystogram, the compartment of the bladder. All right, think about, am I putting it into a compartment? Okay, below is a renal scan with TEC DTPA. What is the mechanism of localization? You know, we have 3 different renal agents. All 3 of them are TEC labeled. All 3 of them are going to be injected in vein, and all 3 have different mechanisms of localization. And it just seems mean, but that's the way it goes. So DTPA is GFR, glomerular filtration rate. The mechanism of location is filtration. MAG3, tubular secretion. Mechanism of localization is secretion. And then TEC-DMSA, that one's active transport. Okay, energy of F18 positrons. Everybody wants to say 511 keV. That's the energy of the annihilation photons, not the energy of the positrons. Positrons all have different amounts of energy when they leave the nucleus. And that amount of energy is going to determine how far it travels before annihilation occurs. Now, is that important? Technically, yes. Clinically, no. So what I mean is, here is your positron emitting. That positron is going to travel a certain distance until it runs out of energy. Once it runs out of energy, mass turns into energy. You have annihilation to annihilation photons. So when I say technically it's important, yeah, because the camera thinks this is where your tumor is, but actually this is where your tumor is. And what is this distance? Depends on the isotope. F18 is real sweet, only 0.3 millimeters. Rubidium, 1.7 millimeters. You heard of the new cardiac PET agent, flurpiridaz? So flurpiridaz, when they come out and sell their drug to your department, that's what they're going to say. They're going to say F18 has less error because rubidium-82 has a higher energy positron. So our images are going to be more accurate. Technically, that's true. Clinically, it's not true. What do I mean? Yeah, you look at physics, that's true. But is it going to make a difference on the patient's outcome, their diagnosis? It's not. So you can call them out on that. Now, I love GE. A lot of them are my friends, and flurpiridaz is going to do great. It's a great product. So is rubidium-82. Nobody's paying me anything except you guys, and I appreciate it. All right, so the answer here is 635 keV, okay? And it's a good idea to know these energies because, I mean, you never know, it could be. I need to make some more flashcards with the energies of positrons. I will do that. All right. Recognition of radiopharmaceuticals on scans. What is the radiopharmaceutical used to make this image? So I think these are the creepiest looking images because I feel like he's looking at me because these are his eyes. Those are his lacrimal glands. And I feel like he's looking at me. I just think they are freaky looking. And then these are the salivary glands. If you see the eyes looking at you like that, then it's going to be a PSMA agent. And so you're like, all right, I know it's PSMA, but I don't see PSMA in your list. And you're not going to see it on your board exam either. You're going to see gozetatide or piflufolastat. That's what you're going to see. So the answer here is gozetatide. It's also fun to say. All right, when comparing an FDG scan with an FES scan, which of the following is true regarding biodistribution? So we need to know the differences. What do they look like? So FDG, look at that brain, hot brain. FES, no brain. Which is actually great for FES because you can evaluate ER-positive lesions that have spread to the brain. The other thing you notice, FDG, look at that liver. You can barely see it. FES, really hot liver. And then the third thing is that vein activity. So if we go back to our question, our choices, the FES will have a hotter liver. Well, that's true. But I'm not just going to give up, okay? I'm like, yeah, I like that answer. I'm going to read the other ones just to make sure. The FES scan will not have bowel activity. Well, let's see. Nope, there's bowel activity. That's wrong. FES lesions will only be hot if they're ER negative. No, they have to be ER positive, so that's wrong. FDG will have very little brain activity. No, there's a hot brain there. So that one's wrong too, okay? So my recommendation, and everybody's going to have different recommendations. Your program director probably gave you a different recommendation. But my recommendation is read the question, think about what you think the answer is, then read all of them, and then pick the answer. But if you think about the answer before you look at your choices, you're going to be guided toward that correct answer, okay? Otherwise, you might be second guessing yourself, because you know what the wrong answers are called? They're called distractors. They're distractors, and it's trying to distract you from the correct answer. So if you go in with the correct answer in your mind, they're not going to distract you as much because you think you already know what it is. All right, theranostic pairs. We have 6 therapies. That's all we have right now. You know, we keep talking about how like we're all great because we're doing all these therapies, and we are. We have a lot coming. Right now we only have 6, okay? And for each of those therapies, there's a diagnostic pair. So make sure you know the therapy and the diagnostic radiopharmaceutical that goes with it. So which of the following is a diagnostic pair for lutetium-177, the pivotide tetraxetan? Question is, what is the pivotide tetraxetan? It's Pluvicto, but it's not going to say Pluvicto on your board exam. It's going to say the pivotide tetraxetan. So then what we have to find is, where is the PSMA agent? You know, it's gozetatide and piflufolastat. Okay, what is the ideal size of TEC-MAA particles? You know how many of you put 10 to 90 millimeters? Because you were taught 10 to 90 microns, right? A micron is not a millimeter. A micron is a micrometer. So it's very important to understand what the answer is instead of memorizing. Because if you're just going to do like where you pair words together, okay? And I try to get my students to not do this. They get mad at me and they're like, you used one word in class and you used a different word on the test. Well, I don't get to pick the words for your board exam. So you have to understand. So when I look at this, what is the ideal size? Well, in my mind, I know it's 10 to 90 micrometers, microns. So I'm looking for something that's 10 to 90 microns. Less than 5 micrometers? No. 60 micrometers? Well, that's in that range. That one's looking pretty good. 10 to 90 millimeters? That's a distractor. Or 100? Nope, this is the best answer. By the way, this is a hemocytometer, and these are MAA particles. And what they do is they put just a little bitty slide. They put a drop of the TEC-MAA on a hemocytometer and puts it under a microscope, and this is what it actually looks like. So it's a qualitative assessment for the size of the particles. They're just looking to see, each one of those boxes are 50 microns. They're just looking to see how big those particles are. All right, another recognition of a radiopharmaceutical. Which radiopharmaceutical normally distributes in the pancreas? Okay, the pancreas. So this one's exciting because we don't have any radiopharmaceuticals that go to the pancreas except for one. So if you see the pancreas, fluciclovine is the answer. Fluciclovine. Okay, the spleen, liver and spleen scan is with texsulfur colloid. Which cells are responsible for the uptake? So, hepatocytes, that's mebrofenin. Also liver cells, but mebrofenin goes to the hepatocytes. The other type of cells in the liver are Kupffer cells. These are also called reticuloendothelial cells, RES, because the RES system. And the mechanism of localization is phagocytosis. And every time I say phagocytosis, I have to do this. And it's because another instructor did that, and now I have to do that. Because that's what phagocytosis is basically these cells, they're going and munching these particles out of the blood, particles that aren't supposed to be there. And so texsulfur colloid particles taken up by the Kupffer cells. Okay, Moly-99 can be made directly through the nuclear reaction, neutron in, gamma out. What is the target material? Okay, so I wrote it out for you here, but if it wasn't written out, the information that you have been given is Moly-99, okay? And you've also been given the reaction, N gamma. And so what we have to figure out is what is going on here, okay? A neutron is going in, this is in, this is what's going out. The only thing that is changing here is a neutron is going in. And if I'm adding a neutron, that means I start with one less. 98 plus 1 is 99. There's no changing of the protons, which means this element has to stay the same. The only time the element changes is if there's a proton change. So our answer is Moly-98. Most Moly-99 is made by fission, but we can make it through neutron capture. All right, radium-223 decays via alpha emission to radon-219. Radon-219 has 86 protons. What is the atomic number of radium? So we have to write this out, okay? So it's telling us radium-223 decays by alpha emission, okay? So it's going to be an alpha, 4-2. And it decays to radon, and it's 219, and it says it has 86 protons. Okay. So we can write all this out, and we can figure out what is this number here, okay? All we're doing is looking at our protons, because that is the atomic number, that's the number of protons. And all we have to do is 86 plus 2 is 88. Because this 88 is going to lose 2 protons when it emits an alpha particle and become 86. So that's your answer, 88. All right, instrumentation. Everybody's favorite category. Actually, almost everybody I talk to, instrumentation is their worst category. And I think I've figured out why, okay? And this is just a theory. But I think we don't like instrumentation because what we're teaching in instrumentation is all the old stuff. We're teaching all about, PM tubes and just really old stuff. And I think it's because all the new stuff is proprietary and it all does everything for you. And so we can't really teach a whole lot about the new stuff because we don't know about the new stuff. And you don't really need to know about it because it does it all for you. So I feel like we just need to lessen the amount of instrumentation we teach altogether. But that's just my opinion. I mean, I would be happy to start a campaign, get a petition going. Maybe we can talk to somebody on the NMTCB or the ARTs, like let's take instrumentation, because I think physics is more important than instrumentation. And instrumentation is like twice the amount of physics. Okay. Which instrument resides in the ion chamber region of the gas ionization curve? This is the ion chamber region. And the answer here is dose calibrator, because the dose calibrator literally is an ionization chamber. So it's going to reside there. The next question is, what would a technologist use this instrument for? Okay. So again, think about what you know the answer is. You're going to use this as a portable ionization chamber. It's on the same area of the curve as the dose calibrator. And the reason is because it measures high amounts of radioactivity. And so we're going to use this for our radiotherapy patients. So we're going to use it to measure how much the patient is putting off. So now I'm going to look for that answer. First one is find contamination after a radiotherapy administration. Oh, I found that word radiotherapy. I'm thinking, ooh, I don't know. Identify removable contamination by its energy. No, that doesn't sound right. Measure the dose rate of a radiotherapy patient. Well, that's just what I was thinking about. That one looks really good. Locate radiation from a minor spill. No, that's not it. So I'm going to go back to this distractor, and now I'm going to figure out why is this the wrong answer. And it's like, oh, I didn't read this. Contamination. Okay. Contamination. We're going to use GM meter for contamination, so this is the wrong answer. This one's correct. All right, a constancy test was done on a dose calibrator. The expected reading was 87 microcuries. The actual reading was 77 microcuries. What should the technologist do? First thing I'm going to do is see if it passed. Right? 10% error is what I'm allowed. My equation is going to be expected minus actual divided by expected. So my expected reading was 87. My actual reading was 77. Divide that by 87, times that by 100, throw that in your calculator, see if you get the same answer as I get. My answer was 11.5%. Did not pass. All right. Document the result and assay the patient doses? No. Apply a correction factor? Nope. Can only do that for linearity and geometry. Can't do that for constancy. Perform a high voltage calibration? I am not fixing the dose calibrator. I cannot do that. Discontinue using the dose calibrator. If it fails constancy, you can't use it. If it fails accuracy, you can't use it. All right, a linearity test is done with technetium. You start with the highest activity that'll be used in your department when you stop the test. So again, I think about, okay, what do I know? I know that I have to keep going until I get to 30 microjoules. So now I'm going to find that answer. When the activity is lowest activity used in your department, I'm a little distracted because I was like, that makes sense. After 10 half-lives elapsed, like, no, Sybil said that's not the answer. When the activity drops to background levels, no, that's not it. When there's 30 microjoules, that's the one I thought. So I'm gonna go back to this one. Be like, yeah, that's not it. This is what I thought it was. So going in with that bias will direct me toward the correct answer. All right, which of the following increases resolution but not sensitivity? So with your collimators, everything you do, if you want to increase resolution, you're going to lose sensitivity. If you increase sensitivity, you lose resolution. It's a trade-off, except in one scenario. And so before I read the answers, I'm going to think, what do I think? It's when I bring the camera close to the patient. Because when I bring the camera close to the patient, it increases resolution, but it doesn't do anything to sensitivity. And tomorrow I'll show you why. And so I'm going to look for that answer. Length of the septa. No, if I make the septa longer, it's going to be higher resolution, lower sensitivity. Size of the holes of the collimator. Well, if I make the holes bigger, it's going to make it more sensitive and less resolution. Distance of the collimator to the patient. That's what I thought the answer was. The thickness of the septa. Now I have to think about that one for just a second. The thickness of the septa. When would we make the septa more thick? Medium, high energy. Sorry about my handwriting. I was supposed to be a doctor, but I never made it. All right. We make the septa thicker, medium, and high energy. When we make the septa thicker, our holes have to be, we can't have as many holes. And if we can't have as many holes, we have to make the holes bigger. So what that actually does is it reduces sensitivity and it reduces resolution. So I thought my way through that, and that is not it. So I know that's the correct answer. All right, you're calculating an integral uniformity based on your pixel counts from this morning's flood. The maximum pixel count is 2,348. The minimum is 2,248, which is true. So what's going on here is you're putting a uniform activity on your camera. Now I only have an 8x8 matrix here. Your matrix is going to be bigger. But you're basically asking each pixel, you're saying, look, I'm giving you each the same amount of activity. How many counts are you counting? And you want them to be really close together because they're all getting the same activity, so they should be counting the same. So if you know what it is you're trying to identify, you can figure out the equation if you forget it. So you want to know how far apart they are. So you want to identify your highest number and your lowest number and figure out how far apart that is. That's going to be in your numerator. So 2,348 minus 2,248. And if you forget what's in your denominator, almost always it's the total. 2,348 plus 2,248, and times that by 100, it gives us 2.2%. So I see 2.2%, and I want to just pick that answer, but don't, okay? Because it might not be the right answer. So we know this one's not it because it says 15%. It says uniformity is 2.2% and does not pass. Now I'm starting to question myself. Uniform is 54%, that's wrong. Uniformity passes, the difference in counts is negligible. That's the correct answer, because I know if it's less than 3 to 5%, it passes. So be careful. If it's a calculation problem, don't just find the number and pick it. Make sure you read the whole thing. All right, this phantom test tests for spatial resolution. What else does it test for? We all know this is a bars test. We're looking at spatial resolution, but did we also know it tests for linearity? Linearity is not just done on the dose calibrator, it's also done to make sure that our lines are straight. So if we get a brand new camera right out of the box and we do a flood, that's what it's going to look like, okay? Because all the PM tubes are going to be different. So an energy correction is going to be done, not by us, but by the manufacturer. And now all the PM tubes are going to be equal. Then a linearity correction is done. And then finally we do uniformity. So when we do this test and test for spatial resolution, we're also checking for linearity to make sure that this test that's done by the manufacturer is holding. Okay, everybody's favorite problem, SPECT acquisition time. Question is, Technologies is performing a SPECT study. Count rate is 120,000 counts per minute. Total counts that we need are 2.8 million counts. And the study is going to have 32 total stops. The question is how many seconds per stop will be needed? So there's a lot here, and it just, sometimes these questions just make me want to cringe because it's like, I don't know where to start. Sometimes starting at the end, figure out what it is they want you to answer in. They want me to find out how many seconds per stop. Okay, well, I already have part of the answer because it's 32 stops. I can put that in here. Now I just have to figure out the seconds. Okay, so whenever you get a problem like this, and now you're stuck again. You're like, I got this far, I don't know what to do. Look for a conversion. Okay, look for a conversion. This is actually a conversion. 120,000 counts equals 1 minute. That's a conversion. And something equals something. Here's the number of counts I need to get, so I'm going to start with that. 2,800,000 counts. Again, conversions are doorways. I put my counts on the bottom, minutes on the top. 120,000 counts in 1 minute. Counts cancel. I need seconds. So close. Minutes on the bottom, seconds on the top. We know there's 60 seconds in 1 minute. We're left at seconds. So now we multiply across the top, divide across the bottom, and we end up with 1,400 seconds. So we can throw our 1,400 in here, and we get 44 seconds per stop. Okay, so sometimes it's just a matter of like block everything else out, say what variable should my answer be in, and you can write that down. Find a conversion. Conversions are doorways. If you find the conversion, then figure out how you get to that doorway to use the conversion. All right, which of the following will decrease the probability of false or random coincidences? All right, in PET, we have 3 types of coincidence. We have what we want, which is our true coincidence. We have scatter, goes off in opposite directions, but this one's going to scatter and give us a coincidence. Sometimes those are called false, but I call this scatter. I call this one false, or random, or accidental, and there's probably a couple more names that I don't know. But what is happening here? I've got 2 annihilation reactions going off in opposite directions, and these 2 are hitting opposite detectors, drawing a false line of response. So the question is how can I decrease the probability of that happening? Well, the only thing that's going to increase it if I give the patient a lot of activity. Because more activity, more annihilations, more probability of getting these falses. So to decrease the probability, I'm going to decrease my activity, which is so counterintuitive, because in SPECT, it's like if you increase the dose, you increase the count, you increase the resolution, everybody's happy, except the patient because they're over-radiated. But in PET, it doesn't work like that. If you increase the dose, you decrease the resolution because you're increasing the probability of these faults. All right, X-ray. Everybody loves X-ray, right? Two X-rays are produced in an X-ray tube that have an energy of 59 and 67 keV. What are these X-rays called? There's only 2 types of X-rays, okay? So in my mind, I'm like, okay, I've got Bremsstrahlung and I've got characteristic. That's a distractor, that's a distractor. And I know that characteristic X-rays are characteristic of the energy between the 2 electron energy shells. And they're always going to be a single energy. So that has to be the answer. Bremsstrahlung is going to be a range of energy. So here are the two types of X-rays. You have an electron that comes close to the nucleus, causing Bremsstrahlung, where you have an electron that kicks an electron out, and when another one falls in its place, you get a characteristic X-ray. Bremsstrahlung is going to be a wide range of activities depending on how close it is to the nucleus. So the closer you are, the more tight that turn is, the more you have to slam on your brakes, or you're not going to make it. The further away, not much of a curve at all. You just tap your brakes, you don't lose as much energy. So that's why the peak looks like this, because this is all Bremsstrahlung, except for our two 57 and 67 kV characteristics. All right, you're scanning a larger patient. What should you do? Increase MA, decrease KVP, decrease MA, decrease KVP. I need to know what MA and KVP are. So, MA, think millicuries. Millicuries is the amount of radioactivity you're giving the patient. The more activity you give them, except in PET, the more counts you're going to have, the better your image. Same with MA. MA is how much radioactivity are you giving them, how many X-rays. And the more you give them, the more information you have, the better it is. KVP, think KEV. This is energy. Now the reason it's KVP, the peak energy, instead of KEV, is because our isotopes are monoenergetic. Technetium, 140 keV. But we just looked at the X-ray peak, and you have a whole range of energies because of Bremsstrahlung. So we report the peak. Now, what does the energy mean? It means the ability to get out of the patient's body. If it's a larger patient, we have to increase the energy. All right, what is the purpose of the collimator? I talk to students all the time, and I don't know why this is. It must be in a book somewhere. But they always say to stop scattered photons. And that's not the correct answer. Scatter lowers the energy, and that's what your pulse height analyzer is for. It's going to block photons that are coming in that are scattered. The purpose of the collimator is to stop photons coming in at an angle. It only lets the ones come in that are coming in straight through, okay? If it's coming in at an angle, it's going to be absorbed by the septa, because we don't want something here to show up over here. That's the purpose of the collimator, not to stop scattered photons. That's the job of the pulse height analyzer. All right, 3 planes inspect. These are them: coronal, sagittal, transverse. Make sure you know them. Most importantly is make sure you can label them. So coronal is how we look at people, also known as frontal. So this is going to be right, this is going to be left, this is going to be either superior or cranial, this is going to be inferior or caudal. Sagittal, side to side, both begins with an S. Anterior, posterior, again superior or cranial, inferior or caudal. Transaxial is the hard one. Transaxial is your patient is laying supine and you're standing at their feet. Okay? And so that means this is going to be anterior, posterior, this is going to be right, this is going to be left. Which brings us to our last category, the largest category, 40% of the NMTCB, is clinical procedures. So again, if all of your scores were about the same, focus on clinical procedures. That's going to give you the biggest bang for your buck. So that's 40% of the exam. Okay, technologist is preparing a patient for a right to left cardiac shunt. Which radiopharmaceutical will be used? Now, we have to understand, I mean, we know it's TEC-MAA, but we have to understand why it's TEC-MAA. Okay? So, TEC-MAA, the size of the particles are such that when you inject, it's going to go on the right side of the heart into the lungs, and it gets trapped in the lungs, and it doesn't make it anywhere else in the body. It just stops. If a patient has a right to left cardiac shunt, that means blood from the right side of the heart is leaking into the left side of the heart, which means that blood is now going to the rest of the body. Where's it going to go? Well, the two most important organs in your body are the kidneys and the brain. Why? Because they get the most blood flow. They get the most blood flow. So that's what you're going to see. And you don't want MAA particles going to the brain or the kidneys because it's going to block off circulation in those areas. And so you don't want that. So if we know a patient has a right to left cardiac shunt, that's why we lower the number of particles. Okay? But if we're doing a study to evaluate a right to left cardiac shunt, we're going to do a whole body scan from head to toe, and we're going to calculate the percent of the right to left cardiac shunt. And again, you have to think about, it's like, I don't want to memorize another equation. So if I understand what I am evaluating, then I can figure this out. I want to know the percentage of counts that are not in the lungs, that are outside the lungs, because that tells me the percentage that's being shunted. So how do I know what's not in the lungs? That's whole body minus lungs. That's everything else. And if I want to know the percentage of that, that's going to go in my numerator, because anytime I want to know the percentage of something, that's your numerator. What's the percent of 24-hour radioiodine uptake? Patient's counts go in the numerator. Percent of a quantitative lung, the right upper lobe. Right upper lobe is going in the numerator. The percent of function from the right kidney is going in the numerator. The denominator is always the total. So that's your equation for calculating a right to left cardiac shunt. All right, a pregnant patient has an order for a VQ scan. All right, I'm going to admit something to you, okay? 5 years ago, I would have gotten this question wrong. I just learned this. I've been practicing for 30 years. And so still, 25 years into my career, actually every day I'm still learning stuff. So quit putting so much pressure on yourself to know everything, okay? Just relax. You have to know enough to pass the exam and recognize you're going to be learning for the rest of your life. So 5 years ago, I would have gotten this question wrong. Pregnant patient has an order for a VQ scan. Why should she get a VQ scan instead of a CT scan? So 5 years ago, I would have said, well, CT scan is going to give a higher radiation dose to the fetus. That's not true. The fetal dose is the same whether you get a CT scan or a VQ scan. Okay? That's the wrong answer. The correct answer is the VQ is going to give the patient a lower radiation dose. And the location of that radiation dose is the female breast. Now, if you're pregnant, your breasts are changing. And what do we know from radiation biology about cells that are changing? They're more sensitive to radiation. Pregnant women, you do not want to irradiate their breasts. So a VQ is going to be less radiation dose to the female breast, and that's why with pregnant patients we do a VQ. Okay. The image below is a super scan. What does this mean? Okay. So the reason it's called a super scan is when we first started doing whole body bone scans years ago, we would do an image of the patient's spine first. And based on the count rate of the spine, that would determine the scan speed, okay? Because we wanted to make sure we got enough counts for the bone scan, and it was based on their count rate. And so everybody moved at a different speed. Now all of our cameras, everybody goes at the same speed, but that determined the speed. So patients that had really bad metastatic disease, their count rate was super high. And because their count rate was super high, the scan went super fast. And so when we were setting these up, we're like, oh, this is going to be a super scan because it would go really fast. I mean, basically you get a whole body bone scan done in like 5 minutes, which was very fast back then. Now we can probably do that. And so that's why it's called a super scan. So it means that this patient has intense osteoblastic activity. Osteoblastic is the building up of bone, and that's what happens when you have metastases. All right, a patient is having a PET bone scan. Which statement is correct? So in this case, we have to read our choices. It's a PET bone scan. After injection, the patient will need to wait 30 to 60 minutes before scanning. Patient will be injected with 25 to 30 millicuries. CT for attenuation will not be necessary. Unlike TEC MDP, uptake will depend on osteoclastic activity. Well, I can rule this one out because we know that osteoblasts are where the aging follows. So we know that's not true. And whenever we do PET, we have to do attenuation correction. So then that leaves me to these two. And it's like, what is the protocol? So make sure you know your protocols going in. The correct answer here is this one. You only have to wait 30 to 60 minutes after injection. So that's a lot different than our Tech MDP bone scans where you have to wait like 3 or 4 hours. The actual dose is only 5 to 10 milliliters. All right, we are on our final half hour. We've been going for an hour and a half. You guys are doing great. So I'm just pausing just to let your mind reset a little bit, get us into the end, going into the end here. And I'm glad that some of you have your cameras on. Nicole, it's good to see you again. And Kristen, it's been a while. Thank you for doing that. All right, here is the sodium fluoride bone scan. Here's the Tech MDP bone scan. Definitely different resolutions, right? So why don't we do all of our bone scans like this? The simple answer is money, okay? That is way more expensive than this. And if you can answer the clinical question without getting a pretty picture, that's what we're going to do. All right, what is the ideal blood glucose level for a patient undergoing a PET CT with F18 FDG? Ideal is the word here, okay? Not what are you doing in clinic, what will you accept? What is the ideal? The ideal is normal, which is less than 120, but that's not the answer because look at my units. So again, you've got to read the whole thing. All right, the 2 most common cancers that require sentinel lymph node mapping, and you're like, oh, I know one of them is breast. Breast, breast, breast. Oh, they're only done for breast. I was like, oh, you're thinking, when else have we done these? Oh, melanoma. That's the answer. All right, this is a renal curve. Renal curve has 3 parts. First part is called vascular, because that's where the blood is flowing into the kidney. Second part, cortical transit. That's where some of it's starting to excrete, but it's still taking up some. That's why the curve flattens out a bit. Third part is called excretion. Question here is, what is the normal time to excretion half time for a renal scan? So what we're going to do is we're going to take the peak, we'll go down half the peak, half time. Here's the peak, here's half time. What is this unit of time? And it's just one of those things you have to memorize. It's 8 to 20 minutes. All right, patient is getting a parathyroid scan using a dual phase protocol. Which lab value would be expected to be elevated? So with a parathyroid scan, these patients, when they come in, they're going to have hypercalcemia. Why is that? Well, here's what happens. It's just like the thyroid, the negative feedback loop. So if your patient has high levels of calcium in the blood, the thyroid's actually involved, not the anterior pituitary. The thyroid is going to release calcitonin, which inhibits osteoclast. Osteoclast breakdown bone, it basically says stop. We've got too much calcium. And so when that happens, then calcium lowers in the blood. And when calcium lowers in the blood, then the parathyroids make parathyroid hormone. The whole purpose of parathyroid hormone is to increase calcium, okay? The whole purpose. And it does that in 3 ways. First way, instead of inhibiting the osteoclast, it actually tells the osteoclast to start working, start breaking down that bone. And that's why these patients come in with bone pain, because their osteoclasts are working overtime. Second thing it does is every bit of calcium that you take in your diet, it's going to absorb it. And the third thing it does is it prevents your kidneys from excreting calcium. So it does all 3 of those things to increase the calcium level. Now, what are we looking at with the parathyroid scan? We're looking at a parathyroid that's gone rogue. That's just going to keep emitting parathyroid hormone. And as it emits parathyroid hormone, it's going to super increase that calcium level. Okay, patient is undergoing a renal scan. Why would furosemide be administered? And I talked to a lot of people from around the country that they're like, well, we give furosemide with all our renal scans. I don't know why we give it. And that's fine. I'm not saying that's right or wrong. But what I am saying is the textbook says that we give furosemide to rule out obstruction. That's what the textbook says. So what does that look like? We have 3 renal curves here. And in all 3 renal curves, we're giving a diuretic right here. When we look at the red curve is normal. It's excreting nicely. We give the diuretic, and now it excretes very fast. Great. Perfectly normal. When we look at the blue curve, it's not excreting. So we don't know if we have a dilated ureter or if it's obstructed. So we're going to give a diuretic. What's a diuretic going to do? It's going to make you produce a ton of urine. So if that ureter, which by the way, the kidney is the only organ I can draw. If this ureter is dilated, and it's just the activity just kind of hung up in the ureter, you produce a bunch of urine, it's going to flush it out, which is what you see here. It flushes it out. So that's dilated, it's not obstructed. But if this ureter is actually obstructed, the green curve, when I give the diuretic, nothing's going to happen. That's obstructed. That is the textbook reason, that's your board exam reason why we give furosemide. It's to rule out obstruction versus dilated ureter. All right, types of imaging. What type of imaging is equilibrium radionuclide angiography scan? I threw this in here not because I didn't think that you knew a MUGA scan was gated. I put it in here to make sure you know that an equilibrium radionuclide angiography is a MUGA. Okay, because we have like 3 or 4 names for everything. I think we should have a consensus conference on terminology. So if any one of you wants to lead that, I would be happy to serve because it's hard knowing all these different terms. All right, let's see. The patient has a heart rate of 75 beats per minute, an end diastolic volume of 145 milliliters, and an end systolic volume of 60 milliliters. Which statement is true? So I quickly look at this and I see, oh, I've got ejection fraction, I've got stroke volume, I have cardiac output. And so before calculating those, I'm going to read the last one just to make sure that's not the correct answer. The patient is at risk of an ischemic response. Well, I don't think that's the answer, but let's go ahead and calculate these. So stroke volume. Stroke volume is your end diastolic volume minus your end systolic volume, which makes sense. Stroke volume is how much is being pumped for each stroke. So our stroke volume here is going to be, I don't know, because I don't have an answer key. 145 minus 75. Stroke volume is 70. Should have been able to do that in my head, but simple math I can't do. All right. So stroke volume is 85. Nope, that's not the right answer. All right, well, kind of forgot how to do cardiac output, so I'm going to do ejection fraction. An ejection fraction is always the big number minus the little number divided by the big number. Okay, so you don't have to remember end diastolic and end systolic, just the big number minus the little number divided by the big number. So when I calculate that, 145 minus 75 divided by 145, ejection fraction comes out to be 59%. That's wrong. Okay, so you know, I'm looking at like 59% is a pretty good ejection fraction. I don't think the patient's having an ischemic response. So even though I forgot how to calculate cardiac output, I know that's the right answer. Okay, wait a minute, I did something wrong. 145. Yep, very good. All right, do we have a hand raise? Billy. Billy's like, you didn't read the question. 145 minus 60 equals 85. Stroke volume is 85. And actually, I do know how to calculate cardiac output. I was just kidding. Cardiac output is the stroke volume times the heart rate. So if you times that by 75, that actually comes out to 6,375. So this one's not the right answer. Thank you for raising your hand, Billy. All right, see, 30 years, still make mistakes. Okay, below are 60 minutes of a HIDA scan. At this point, what conclusion can be drawn. So I see 60 minutes, I'm seeing liver, I'm seeing gallbladder, I'm seeing bowel. The only thing that I can rule out here is acute. It's not acute cholecystitis. It's not acute gallbladder, because all gallbladders are ugly. I always have to pause there because it takes a second, okay? It's not acute gallbladder because they're all ugly. If you see the gallbladder at any time, it's not acute. You've ruled it out. All right, so at this point, what conclusion can be drawn? The patient is not normal? The patient could still be normal. Patient has a blocked cystic duct? Nope, I see the gallbladder. Patient may have a sphincter of Oddi dysfunction. I don't even know what that is, so I forgot. Actually, that's not true, but maybe that's what you're thinking. Patient may be normal or have chronic cholecystitis. Well, at this point in the scan, I'm given CCK, and why do I give CCK? To see if they're chronic or normal. So that's my answer. All right, patient was given CCK and images were taken. Calculate the ejection fraction using the following information. Again, I don't need to know which is which. I just know this is ejection fraction. Big number minus small number divided by big number. When I do that, 85,456 minus 46,425 over 85,456, always times by 100. My answer is going to be 46%. All right, I love this question. A patient is injected with 3.5 millicuries of texsulfurcolate. If the patient has normal biodistribution, how many millicuries will go to the liver? So what this question is actually asking is what percentage goes to the liver, what percentage goes to the spleen, and what percentage goes to the bone marrow. The liver is 85%, the spleen is 10%, the bone marrow is 5%. So if 85% of this is going to the liver, I just take 3.5 times 0.85, and that's going to give me 3 millicuries. All right, prior to administration of Y90 microspheres, which by the way, Y90 microspheres are particles just like TEC-MAA, and they're about the same size. So prior to administering these microspheres into this patient's hepatocellular carcinoma, we're going to inject TEC-MAA because we want to know if this leaks out into circulation. Somebody's got a hot mic. If it leaks out into circulation, it's going to be picked up and taken to the lungs, and we're going to irradiate those lungs. So we're going to inject the MAA. Actually, we're not. We're going to bring it to IR, and we're going to give it to the physician. The physician's going to inject this because it's intra-arterial, and we do not intra-arterially inject anything, not on purpose. We could do it by accident. So we want to know what is the percentage of these counts that are going to the lungs. Again, whatever is you want to find the percentage of that goes in the numerator. We're going to put 18,000 in the numerator. Denominator is going to be the total, 262,000 plus 18,000, and we'll times that by 100. In this case, it comes out to 6.4% shunting. Now, is that okay? Yes, but there's another way that the package insert defines how much can go to the lungs. You're preparing a patient for Y90 microsphere therapy. According to the package insert, what is the maximum amount of radiation that can be given to the lungs? The package insert says 30 gray. And that is just confusing, right? Well, we're giving the patient about 120 gray, okay? And so we can take that fraction that's going to the lungs and multiply it by 120 gray. And if it's less than 30 gray, then we're okay. If it's more than 30 gray, we can potentially lower this dose. And I know it's confusing because like we administer millicuries, we don't administer grays. Well, we don't have to do this, but you can take the grays and convert that based on the size of the liver lesion and convert it into millicuries. And that's how we determine how many millicuries to get in order to get 120 grays to that site. All right, almost done, 15 minutes. Patient is injected for a PET interictal scan. Which radiopharmaceutical was injected? Before I look at my distractors, I'm going to think about this. Interictal, all right, seizure, what are we going to use? We're going to use FDG. I'm going to find the FDG, and then I'm going to go back and read the other ones. I'm like, oh yeah, that's a good distractor. Fluorodopa goes to the brain, but it's for Parkinson's. Oh, for Betapir, that's Alzheimer's. For Firdaz, that's cardiac. What type of scan is done to evaluate the presence of normal pressure hydrocephalus? Again, before you look, think about what the answer is, because all these look really close together. And I know it's cisternogram, because we're looking at the basal cisterns. That's normal, trident sign. Abnormal, heart-shaped sign. Patient is scheduled for a CSF leak study. How are we going to inject the tracer? Well, our patients come to us with these pledgets up their nose, okay? They're just cotton on a string. They come, we don't have to put them in, but we do have to take them out. I've never done it, but that's what we do. So we're looking to see if their CSF is leaking. So we have to make their CSF radioactive. How are we going to do that? We're going to intrathecally inject the Indium-111 DTPA, not us. We're just going to walk in with the vial and say, here you go, you do it. Which of the following ECG patterns is associated with myocardial infarction? All right, so when we're looking for infarction or ischemia, we're looking at what's called the ST segment in between the S and the T. So we call this baseline here. That ST segment is right on the baseline. If we walk through here, you can see the ST segment here is elevated, and on this one, you can see the ST segment is depressed. So, elevation goes with infarction. This is what you're trying to find on the treadmill. That's an ischemic response. You see that, you stop the treadmill, you send them straight to cath lab, you're not even taking pictures, you're done. You've got your answer before you have to take pictures. All right, we have a few left. We'll probably finish a couple minutes early. Open it up for questions. Which type of medication is used for a patient who had a dobutamine stress test and their heart rate will not come down? That is called the beta blocker. Ends in LOL. It's not funny, but LOL. It's also really good for public speaking, okay? Because what it does, I mean, most of you are students, you've given presentations in your class, and what happens when you give a presentation? Your heart starts beating real fast and you can't breathe, and like you just take a beta blocker, it does the same thing, keeps the heart rate low. And I'm not saying I did or didn't take a beta blocker before this, because I still get nervous public speaking. Not going to admit it or deny it. All right, a patient is having a quantitative lung scan. The total right counts are this number, the left counts are this number. I want to know the percentage in the right upper lung if it's that many counts. Again, whatever you want to find a percentage of, that goes in the numerator. So we'll put these counts in the numerator. The denominator is the total of these two. Comes out to 6%. What would be included in a patient history for someone getting a lung scan, a VQ lung scan? Well, there's basically three risk factors, or three categories of risk factors. Okay, if you can remember these three, then you're good. First one is sedentary. A lot of things can cause you to be sedentary, right? Cancer, recent surgery, long flight, anything that causes you to be sedentary. Second one is smoking. And the third one is hormones. All right, any women that have gone in and got on birth control pills, they drill that into us. Like, you're going to increase your probability of getting a blood clot. We're like, okay, I'll take that risk over getting pregnant. Hormones, but there's a lot of places that you take hormones, okay? Not just birth control pills, but also pregnancy, postpartum, hormone replacement therapy, so hormones. So out of all of these, do any of them fall into one of these categories, recent surgery? All right, below is a transverse slice. Which label would go on the bottom? Okay, this is transverse, patient is supine, I'm standing at their feet. So if they're supine, that is going to be posterior. Technologist is processing a HIDA scan. Draws an ROI around the gallbladder. and then graph the counts. What is this graph called? Time, activity, curve. And look at this distractor here, gallbladder curve. That's not the right answer. Time activity curve. They won't do that on your board exam. I didn't even realize that was there when I wrote the question. All right, this is our last one. Gallium-68 dotatate is used for neuroendocrine tumor imaging. Which SPECT agent is used for the same purpose? And I just heard about somebody doing this not long ago. It was a patient that was 2 hours away from the nearest PET scanner. And the physician was like, well, let's just do this scan, Octrio scan, otherwise known as indium-111 pentatriotide. And they did, and it turned out fine. All right, so this is what indium-111 pentatriotide looks like compared to DOTATOC and dotatate. So that's why we don't really do these anymore, because we get much better images with these. All right, that takes us to the end. Tomorrow we have a big day. At this point, I'm going to stop sharing and open it up to any questions. Also, if you'd like to turn your cameras on, that would be pleasant, because I know many of you. There's Haley, Michelle, Tanner's in clinic, Nelson, met you just the other day, Brittany, Avery, Wings, been a long time since we've met. Very good. Lisa, you emailed this morning. Any questions?
Sybil, we have a question on the chat. How do we access those flashcards you mentioned? They made an account on your website.
I'm getting ready to go on the account and give everybody access. I used to leave it just for people who were my actual clients, but I've decided that, no reason to keep that hidden. I'm going to give it to everybody that wants it. So if you've made an account currently or in the past, you're going to get a message from me. It might go in your spam folder that basically says, go ahead and, log in, fill out a password or something. If you have any trouble, send me an email. Yeah. And then you click on member dashboard, and the flashcards are probably what most people are using, but there's a couple other resources. And, I just started doing this. As I get more resources, I'll put those up as well. I was scared for a second. I thought you were going to give me a hard question.
There's another question in the chat. Can you still get ST depression when you get artifact on the treadmill?
Get artifact on the treadmill. So like if you're getting EKG changes, and is the ST depression like real or artifact? I think that's the question. I don't know the answer to that. I guess it kind of depends on, how good is the tracing. Sometimes we get a bad, connection, and so the EKG looks wonky, or they might have some other EKG changes that make it difficult to identify. The two examples I gave you are extreme examples, so it's usually not that easy to see. But I would say that if it's true depression, then it's not an artifact, and they would go straight to the cath lab. Do we have any questions about tomorrow? Kimberly, you have your hand raised.
Yeah, it's because I can't access the chat on here for some reason, but I just wanted to know, is it possible, or is there a way we're able to possibly retake the mock? It was a lot dear when I was taking it. My daughter was full time, so I wasn't able to very much pay attention.
I do have another version of the mock exam. If you set up a strategy call with me, we can discuss that.
Okay, I set one up with you for Monday. Thank you.
Oh, okay, great. I'm looking forward to meeting with you. All right, what else? So if you're not graduating for a while, I have another review session I'm doing in December. I know some of you were here in the spring one as well. All right, how do we set up a call with her? Go to the website, the Nuclear Professor, because there's only one, thenuclearprofessor.com. And there's a link on the first page that says set up a free 15-minute strategy call. And Lisa.
Hear me?
I can.
Hi. If we are graduating soon and we like to do more mock exams, is there anything we can access?
Have you done the quizzes on my website?
No.
Okay, let me show you those real quick. All right, so on the website under mini courses, I've got a free quiz under each of the sections. And then there's a quiz for math, and then there's one clinical procedures quiz. And you'll get the results right away.
Okay.
That's absolutely free.
All right. Thank you.
You're welcome.
Sybil, another question in the chat. Is there a way to access the answers from today's meeting? I missed a few questions.
If you took the mock board exam, you should have gotten your results, and it should tell you what the answers are, and the correct answers and the wrong ones. If for some reason you don't, send me an email, because maybe if you didn't finish the mock board exam, you can still take it at this point, and it will release your results to you. Is there another question?
Is there a way to set up a class when the only availability is after you take your boards?
Right, my classes don't start until August 6th, and then they run through November. That is a good question. You can always set up an individual class with me. I have single tutoring sessions. If you would like to meet with me one-on-one, you can certainly do that. So tomorrow's going to be a lot of fun. I'm really looking forward to the Kahoot game. It's brand new, so nobody has seen it yet, so there's no way that anyone is going to have any kind of advantage. I do have some trivia questions within the Kahoot game, so even if, maybe you're earlier in your program, the trivia questions are the great equalizers because nobody knows those. And so it's anybody's game as who wins that.